We're going to begin homework number 8 on circular motion with some conceptual questions here. So for this first one, we have a ball rolling around a tube as shown, and we want to know the path it takes after it exits the tube. So while it's in the tube, we have an inward force causing that inward centripetal acceleration to keep it moving in a circle. Once we exit the tube, the ball discontinues having that force, and so it's just going to continue in the direction it was initially moving, which, if you remember your concepts about the velocity of an object traveling in a circle, that velocity is always tangent to the circle at any point. So the path that we'll take will just be a straight line path from the end of the tube. Moving on to the next one, we have a go-kart traveling around the curved track as shown at a constant speed. And the first thing we want to do is draw the direction of the acceleration at 3 points, A, B, and C. Keeping in mind that it's moving at a constant speed, the only way for it to accelerate would be if it's turning. If it's moving at a constant speed, it can't speed up or slow down, so it has to be that changing directions acceleration. So at A, we are turning. We're going in a circle. The center of our circle is here, so our acceleration is inwards towards the center of the circle. At B, same thing. We're turning. The center of our circle is there, so our acceleration is also inwards because we're turning at that point too. For C, we aren't turning, we notice, and so because we're traveling at a constant speed and not turning, that means we are not accelerating, so our acceleration at C is just 0. We're now going to rank the magnitude of the acceleration in these situations. So we're going to keep in mind that while an object is going around in a circle, its acceleration is given by v squared over r. So looking at A and B, those are both situations where we're accelerating. Obviously C is the lowest because there is no acceleration. But between A and B, B has a smaller radius than A. They both have the same speed, so that top term is the same, but we're dividing by a smaller radius, which means the acceleration at B is greater than the acceleration at A, because A is a bigger radius, and they're both greater than C because C is an acceleration of 0. For our next one, we have an object swung around in a vertical circle at a constant speed, and we want to know if the tension in the rope at the top of the circle is greater than, less than, or equal to the tension at the bottom. So I'm first going to draw a free body diagram showing the forces acting on it at both the top and the bottom of my circle here. So at the top of the circle, I have the force of gravity going down, and I also have the force of tension from the rope going down. That's leading to that inward acceleration towards the center of my circle. At the bottom, I have the force of tension going up and the force of gravity going down, and I'm also accelerating inwards, but in this case that acceleration is up. So if I look at these forces here, I can see that at the top, Ft and Fg are working together to create that inward acceleration, whereas at the bottom, Ft has to oppose Fg and still add some additional force to create that inward acceleration. So that means this tension at the bottom is going to be bigger than the top. So to answer the question, the tension at the top is less than the tension at the bottom. And so the first thing I would say is at the top, both Ft and Fg combine to create that inward acceleration. And at the bottom, Fg opposes Ft. So that means that Ft must balance that force of gravity there and then create an inward acceleration on top of that. We're going to move on to some algebraic problems here. So up first we have a bicycle going around a track, a circular track with a radius of r, and we know the coefficient of static friction between the bike and the track is mu. The bike's going around at a constant speed, and we want to know the shortest time the bike can go around the track without slipping. So let's start with the free body diagram here. So once again, I'm going to take advantage of the side view, which is what we typically do when we have an object going in a horizontal circle here. And so in that case, we have the force of gravity going down on the object, the normal force going up, and I'm going to say it's traveling in a circle like this. Again, that velocity is coming out of the page. So that means the force of friction is the force keeping it moving in a circle, causing that inward acceleration towards the center of my circle here. So we're now going to go ahead and set up our max and our may. So in the x direction, we have the force of friction, and and that's going to be equal to ma. Two substitutions I can make here. My force of friction I know is going to be at a maximum because we're riding around in the shortest amount of time. We're traveling as fast as possible around this track without slipping. So I can say that the force of friction is simply my coefficient of static friction times my normal force. I also can substitute in for my acceleration because I know that anytime I'm traveling in a circle, my acceleration is given by v squared over r. Setting up my y forces, I have Fn minus Fg, and that's going to be equal to 0 because we're not accelerating vertically, okay, just horizontally. And so my normal force then is equal to Fg, which is simply mg. I can go ahead and substitute in for my normal force. I also know that my coefficient of friction, coefficient of static friction, is just given by mu, so I can say mu mg equals m times v squared over r. My m's will cancel out. And I ultimately want to get the shortest time that I can go around the track, so I'm going to first find the velocity of this object as it goes around the track. So solving for velocity, I get mu gr equals v squared, so the square root of mu gr is equal to my velocity. Now that I've solved for that velocity, I can use that velocity, and I know that when an object's traveling in a circle, its speed, or the magnitude of its velocity, is given by 2 pi r over t. So I can substitute in that velocity I just solved for, mu gr, for the velocity in this equation, and then I can go ahead and I can solve for t. So t is the time for one period, or the time to go around the track one time. And that's what I'm ultimately looking for. So I'm just going to rearrange this equation by cross multiplying first of all. So I get t times the square root of mu gr, and that's equal to 2 pi r. And then I go ahead and solve for t, and I get that t is the square root of mu gr over 2 pi r. Moving on to this next one, we have a situation where there's a puck sitting on a table, and the puck's going to be going around in a circle on a table that is frictionless, and it's connected to a rope with this hanging mass that's just remaining stationary. Okay, so puck's moving around in a circle where the mass is just hanging down and actually providing that tension to allow the puck to move around in a circle. So first thing I'm going to do, like I do with any of my force problems, is I'm going to set up a free body diagram, and in this case I'm going to set it up for both objects. We have two objects, so we're going to have two free body diagrams. So for the puck, we're going to have the normal force going up, the force of gravity going down. Once again, this is the side view here, so we're thinking about it traveling in a circle like that. And then we have, in this case, the force to keep it moving in a circle is the force of tension going inwards, leading to that inward acceleration. For the other object, the hanging block, we're going to have the force of tension pulling up on it, and we're also going to have a force of gravity acting down on it. I'm going to call one of them Fg1 and the other Fg2 just to distinguish between the two. And this one we know is just remaining at rest, so its acceleration is 0. So this one's a little bit different than some of the system ones we did where they were accelerating together. Here they actually have two different accelerations because one's hanging at rest, the other's traveling in a circle accelerating inwards. I'm now going to go ahead and set up my F equals ma for each object. For the puck on the table, I really only care about my x forces. I could do my y, which would tell me that my normal force equals that force of gravity, but because we're not dealing with friction, that doesn't actually matter here. So I can just say that Ft, that force of tension, is equal to m, and I'm going to substitute in big M because that's what its mass is, times this acceleration, which is v squared over r. Okay. For the other one, for the hanging object, we're going to have Ft minus Fg2, and that's going to be equal to 0 because my acceleration is 0. So I can say that Ft is equal to little m, the mass of this object, times g. I can now go ahead and combine those two equations, so I can substitute in Ft into my equation for the puck, and I can just say little m times g equals big M times v squared over r. I'm ultimately looking for how fast the puck is traveling, so we want to find this velocity here. So I'm going to solve for that. So what I'm going to do is I'm going to first multiply both sides by r, so I'm going to have rmg, and then I'm going to divide by big M. So rmg over big M equals v squared, which means that v is the square root of that expression, rmg over big M. Moving on to this next one, we have a situation here where we have a bucket being swung around in a vertical circle attached to a rope of length L. So something like this would be the motion of the bucket. And here is our rope with a length of L, and we want to know what is the minimum speed the bucket must have at the top here so that the water doesn't fall out, similar to the demonstration that we did in class. So if we think for a second about the forces acting on the bucket, we're going to have the force of gravity going down on the bucket, of course. We're also going to have a force of tension from the rope going down on the bucket, and both of those lead to that inward acceleration that we have. When I go to set up my F equals ma here, I'm setting up my F equals ma in the y direction. I'm going to have ft plus fg is equal to m times v squared over r. And so we want to derive an expression for the velocity of the bucket, but we have a little bit of a problem here, and that is this force of tension. Okay, we don't really know anything about that force of tension, so we need to think about our concepts for a second. And we do have this hint here: when the speed is a minimum, what is the force on the rope? So as this bucket's being swung around in a vertical circle, imagine it going slower and slower and slower. What's going to happen to our forces? Well, gravity can't change. Gravity has to remain the same. But our total force has to get smaller because we're not traveling as fast. So what ends up happening? That force of tension gets smaller and smaller. We eventually hit this point where there is no tension. And if we had gone any slower, what would have happened would have been the rope would have had some slack in it. It would have looked something like this at the top of the circle, and it wouldn't have been a nice taut rope that's actually pulling on the bucket. In that case, the tension is 0. So at this point where we're going as slow as possible, there's this perfect speed where the force of tension does not actually act on the bucket itself. And only the force of gravity at the very top, that's the only force keeping it moving in a circle. And so once we get rid of that force of tension, we can make this substitution here, mg equals m times v squared over r. Our masses cancel out here, and we can solve for r in terms of L, the length of the rope, which is the radius of our circle, and fundamental constants. So I can just say g times the radius equals v squared. The radius is L, so g times L equals v squared, which means my velocity is the square root of g times L. Moving on to this next one, we have a car going around a banked curve. The curve has a radius of r and is banked at an angle of theta. And we want to know what speed the car can go around this curve so it's able to safely navigate the curve without friction. All right. So first we're going to start by drawing our free body diagram. And we are going to draw our curve as banked, and we're going to remember our important trick here when dealing with a banked curve. So here's our car on the banked curve. We have the force of gravity going down on it, and we have the normal force acting up at an angle perpendicular to our curve. This is a side view here, like we do with any horizontal circle. All right, so our car is traveling in a circle that looks something like that, which means it is accelerating inwards. With this situation, this is different than inclined planes. It looks very, very similar, but the key difference is we're not accelerating up and down the banking. We're accelerating inward and actually keeping in the same position along the banking, just accelerating inward because we're turning. So it's a very different situation than an inclined plane, even though it looks similar in setup. So what we do here is we do not tilt our axis, okay? So gravity going straight down remains in the y direction. We're using our regular axis where y is vertical and x is horizontal. So gravity is not at an angle. However, our normal force is at an angle. Okay, so we have one component of our normal force going up, one component going to the right. And the angle of the banking of the curve, all right, ends up being that angle, that lower angle there in our components of the normal force. So I'm going to componentize that normal force, so that means this y component ends up being Fn cosine theta, and the x component ends up being Fn sine of theta. And now that I have that set up, I'm going to go ahead and set up my max and my may for this situation. So in the x direction, I have Fn sine of theta, and that's going to be equal to m times my acceleration. That is that centripetal acceleration, so it ends up being v squared over r. In the y direction, I end up with Fn cosine of theta, that vertical component of the normal force, minus Fg, and that's equal to 0 because the object is not accelerating up and down, it's only accelerating inwards due to the fact that it's traveling in a circle. So that means that Fn times cosine of theta is actually equal to mg. And so I have these two equations, and I'm ultimately going to need to combine these two equations to be able to solve for this velocity, because we need it in terms of r, theta, and fundamental constants. So we somehow need to get rid of this m. We somehow need to get rid of that normal force there. So this is what I would be thinking about, and there are a few ways of combining it. I could just solve this equation for Fn and substitute it in. But what I see is there's this cosine of theta and there's this sine of theta, and I know that sine of theta over cosine of theta equals tangent of theta. So what I think is a really, really nice thing to do is take that x equation, Fn times sine of theta equals mv squared over r, and divide it by that y equation, Fn cosine of theta is equal to mg. And like I said, this isn't the only way of doing it, but I do think this is a really nice technique because our Fn's cancel out there, our m's cancel out there, and what I'm left with is sine of theta over cosine of theta, which is just tangent of theta, is equal to v squared over r all over g. Okay, we do have a double fraction there that we can rearrange by multiplying top and bottom by r, and so I really get v squared over gr. What I'm going to do is I'm going to go ahead now and solve for v. So I'm going to multiply both sides by gr, so I have gr tangent of theta equals v squared. I take the square root of both sides, and I get that v is the square root of gr times tangent of theta. And that represents that perfect speed where the car can travel around the curve without sliding up or down without any friction needed. Now in reality there would be some friction, and that just gives the car some wiggle room. So if it's a little bit faster or slower than that perfect speed, it still is going to be able to safely go around that curve. For this one, we have a car traveling around in a circle on a level track at a constant speed, and we want to know how the acceleration changes when there are a few different changes that happen to the motion of the car. So this is one where we want to set up our original situation and then a bunch of new situations. So our original situation is that our acceleration equals v squared over r, the magnitude of the velocity or the speed divided by the radius. And so we're going to set up a bunch of new situations and do a comparison each time. So for A, we're told that the velocity is tripled, or the speed is tripled. So I'm going to say that A prime, my new acceleration, is equal to 3v, that entire quantity squared, over r. So A prime is equal to 9v squared over r. There's a few different substitutions we could make here, but what I'm going to say is I'm going to just pull out that 9 and say A prime, my new acceleration, is equal to 9 times v squared over r. I know that my v squared over r is simply equal to that original acceleration. So for this first one, my new acceleration is 9 times my original acceleration. This is one where if you had just reasoned your way through it with the fact that acceleration is directly proportional to v squared, you could say that if the speed triples, the acceleration will increase by a factor of 3 squared, or 9. That would work as well, but we can do it mathematically too. For b, the acceleration changes because the radius of the track is halved, so I'm going to say a prime is equal to v squared over 1/2 r. I'll get rid of that double fraction by multiplying top and bottom by 2 here, so a prime is equal to 2v squared over r. I'm going to pull out that 2 once again, so a prime is 2 times the quantity v squared over r. Once again, I know that v squared over r is simply equal to my initial acceleration, so I can say a prime is equal to 2 times a, that initial acceleration. Once again, using logic, that r is cut in half since a and r are inversely proportional. If our radius is half as much, that means that our acceleration is twice as much. Moving on to C, we have the mass of the car is doubled. And so we think about our equation here, a equals v squared over r. There is no mass in there at all, and the mass certainly doesn't affect the velocity of the object or the radius, so that means that my new acceleration in this case is just equal to my original because mass doesn't affect it. Moving on to D, the period of revolution is halved. So at first you might say, well, period's not something that's given at all in this equation. It's just v squared over r. Period's not even in there. However, we have to keep in mind that period affects that velocity. And the reason we know this is that my velocity is given by 2 pi r over t. So this one's actually a two-step problem. So I'm going to say this is my original situation. My velocity is 2 pi r over t for my car originally. And I'm going to think about my new equation for my velocity, v prime. So the period is cut in half. So I'm going to say v prime is 2 pi r over 1/2 times t, that initial period. I'm going to multiply both top and bottom by 2 to get rid of that 1/2. And so what I'm left with is v prime equals 2 times 2 pi r over t. I could have written it as 4 pi r over t, but what I want to do is I want to pull that 2 out. And so I'm going to say v prime is equal to 2 times this quantity, 2 pi r over t. That happens to be the same as my original velocity, so I can say for my first step that my new velocity is just 2 times my original. And now that I have that set up, I can think about my acceleration. So I can say a prime, my new acceleration, is v squared, which is now 2 times my original velocity, squared over r. So a prime is 4v squared over r. Pulling out that 4 once again, I have a prime is 4 times v squared over r, which was my initial original acceleration. And so that means that my new acceleration now is simply 4a. Okay, so this one is a two-step problem. We first want to figure out how my velocity changes when the period's cut in half, and then we can go ahead and see how that ultimately changes the acceleration. So really saying the period of revolution is halved is another way, or more complicated way, of saying that the velocity is doubled, and then we just go from there.